Okay, so if there are no questions about the exam, we'll start with today's lecture. But before that, if you've seen the syllabus, you'll see that you've pretty much done 2 assignments, and the third assignment is a few days from now. I mean, in the sense, I think it's released on right before spring break, and I think it has 3 weeks or 4 weeks, 3 or 4 weeks duration. So it's a little bit longer than the previous assignments. I think there are 1 or 2 questions more. But the thing is, right now you don't have any assignments. That doesn't mean the course is going to be easy. So the thing is, there's a big percentage of points for first project report and the second project report. So you want to kind of do well there. That's why you have a lighter load in terms of assignment. Okay. So do try to make progress on your project reports. That's yeah.
So I told in class, is there any way you could move the project report from Friday night to
Project reports to Saturday?
The due date?
Yeah, can you send me an email and
Yeah,
I'll look at it.
sure.
If everybody wants that, that's fine. Okay. The final exam is on 5th of May, which is right before the finals week, so that some of you, I don't know if anybody is graduating, but I think 12th is the commencement for some of the students. Okay. So today we're going to look at we're going to continue looking at some topics which are not directly related to supervised learning. So the context is we were looking at supervised learning. And we saw several linear methods basically, as well as KNN. Okay, so there are a bunch of methods in between. So there's linear methods on one end of the spectrum towards the left, and there's KNN, which is quite flexible, towards the right, and there are a bunch of methods in between. And this is going to be the content of I think next 2-3 lectures. Okay. So we'll look at something called SVM, which you might have heard of, random forest, and a few others which I'll not name now, but we'll see some methods which are not just linear. Okay. So SVM in the most vanilla version is actually linear, but there's something else, some other thing that you can add on to SVM to make it non-linear. Okay. So we'll look at methods in between. Now last class we were looking at maximum likelihood estimation. As a way of relating supervised learning loss functions, like squared loss is related to making some Gaussian assumption about your data, right? We saw that. So maximum likelihood estimation is all about defining a likelihood function, or log likelihood function, log of the probability of data. So okay, let's see. Let me use. So data can be X only, or I'm going to use Y just an arbitrary choice, given parameters. Okay, something like this. So this would be the likelihood function. It need not be a vertical line. It can be something like a comma. Okay, and then there's you want to maximize over parameters. Okay, for example, if you're fitting a Gaussian, it's going to be the mean and variance that you're trying to maximize. And if it's a simple function, then we know that, for example, if it is actually a Gaussian distribution here, okay, you're just trying to fit a Gaussian given data, right? Then you knew that okay, so the actual problem if you had data would be something like a sum over I is equal to 1 to n, the probability of y is equal to little yi for a parameter theta, and let's say it's Gaussian, so theta will be 2-dimensional, mu and sigma square. Oh, sorry, there's a log missing. maximize over theta, which is essentially that, maximize over mu and sigma square. Okay. And we saw that, the best, if you would actually maximize, as in take the derivative of this, actually substitute what is the expression for Gaussian distribution, log and exponents kind of cancel, and you'll have a squared term, and essentially, here I'm looking at one-dimensional Gaussian, so you will get a estimate, whatever maximizes. I'm going to use argmax to denote something which maximizes. So let's say that's mu hat and sigma hat square. So mu hat, for example, was just 1 by n sum over I is equal to 1 to n of yi's, right? Just the empirical mean. If you had n data points, just take the mean. That is the estimate of your mean of your Gaussian, right? That's quite intuitive. This is what we did last time. So just coming back to the point, we were looking at linear models. That was the first 5 lectures essentially. In the future, we're going to look at SVMs, RFs, and so on, random forests, and so on. And finally, we'll look at, so that was supervised learning, and finally look at unsupervised learning. In between, last class, we looked at maximum likelihood estimation and bootstrap. Today, we're going to look at further extending maximum likelihood estimation. So, and this is going to be a key tool. So today, we're going to look at extending MLE. Okay. So that's one thing that we'll do. The second thing we'll do still, which is not completely. So MLE is a bigger set of problems than just supervised learning. That's what I want to kind of orient us towards. And extending MLE is also going to address bigger set of problems. And then we will also look at another interesting tool, just like we saw Bootstrap last time. We'll look at another tool called Gibbs sampling. Okay, and I'll motivate these two tools today, and then we'll get back into supervised learning. So it's a good digression because we did a bunch of linear models in both for classification and regression, and then we took a digression to relation to MLE. We'll see that MLE is just a very general framework, and today we'll see a particular we'll see a problem with just doing MLE. It's computationally difficult, and so we'll look at extending MLE, and that's that method or technique is called expectation maximization. And related to MLE and EM, whatever, is going to be a technique which is called sampling. And sampling just means drawing random numbers from some distribution. Maybe drawing random numbers from a uniform distribution is easy. Maybe from a Gaussian it's easy. Maybe you have function calls in R and Python, for example, to do so. But it's going to be difficult for arbitrary distributions, and we'll see one example today. And so these two are interesting tools, and then we'll get back to supervised learning with nonlinear models. Okay. Any questions about the trajectory, the lay of the land? Because from now onwards we'll lose the lay of the land and focus on the topics themselves. Okay. Somehow this guy is not. So why do I want to extend MLE? So MLE was just what I wrote earlier, right? The problem. Let's say I observe a data. So this is just a motivation for EM. So the way I'm gonna kind of define this EM method, it's gonna be like MLE method. MLE method is just saying write down the likelihood, take its log. Log is just for convenience, and maximize it. Okay. Now I'll motivate EM using an example, and then towards the end I'll give you the general template of how to do EM, and also justify the name why it's called expectation maximization. But we'll get there. So let's say, so in terms of motivation or as a special case, let's think of this data set. It's one-dimensional. Okay, and it's going to be one-dimensional data set. So some observations that I'm seeing. Okay, some bunch of observations. It turns out that if you just draw the histogram, okay, it is not unimodal. Okay, let's say you drew the histogram, just bin the number of points falling into each interval. It turns out to be, it has two peaks. Okay, now just by eyeballing, because it's one dimensional, you can say that maybe I can fit it using two Gaussians. Okay. Okay. And one way to kind of say that the data follows two Gaussians, is the way is called defining a Gaussian mixture model, and it's gonna be as follows: that so there's going to be two Gaussians involved. So let's say y1 is the first Gaussian. So maybe it's Gaussian I'm representing as that mean mu1 and variance sigma 1 square. Okay. There's going to be another Gaussian y2, which is also mean mu2 and sigma 2 square, right? The two Gaussians. I'm also going to introduce another variable, delta. It's a random variable. So all these are random variables, right? Which is going to be Bernoulli with the parameter pi. Okay, so I'm going to use pi as just a symbol. It's not the 3.14 stuff. So with these three random variables, I'm going to define a derived random variable. Just means this new random variable is just a function of the previous ones. So let y be equal to, what is the notation use? Okay, 1 minus delta times y1 plus delta times y2. Okay, so I'm multiplying random variables here actually. Okay, and this data that I see, I'm gonna say that this data is actually realizations of this random variable, derived random variable. Okay, so this is a specification of a Gaussian mixture model. It's basically saying here the order doesn't matter. Maybe I can put this delta guy at the top, just to read it from top to bottom. I can say I'll flip a coin with bias pi. Maybe it lands heads, maybe it lands tail. Delta is a Bernoulli random variable, takes value 0 and 1. Maybe it takes value 1. Then essentially I'm picking, if it takes value 1, I'm picking y2 as the y that I observe. Okay, I'm seeing an observation from the second Gaussian. And if delta happens to be tails, then I'm seeing an observation from the first Gaussian. Okay, this is called I guess this is called a generative description of the data. Generative description of the data. The data that I observe is only these y's. Okay, these are this random variable, and this random variable I'm saying I'm roughly hallucinating or modeling that this random variable happens because there is some unknown, or I'm just conjuring that there is a random variable delta. If it lands heads or tails, depending on that, I'm picking I'm getting a sample from one Gaussian or the other. Okay. Any questions about this part? No, delta is a random variable. Yeah.
And the sum of both the delta should be 1.
There's only one delta random variable here. Yeah, it's Bernoulli. It only takes value 0 or 1.
In case of prime order, then how would it
If there are three Gaussians. So then delta will not be Bernoulli. There is an extension to Bernoulli called the categorical variable. I don't know if you've seen. It's just a fancy name to say three outcomes, 0, 1 and 2. That's all. Maybe you've heard of multinomial random variable. Okay, there are different very, I guess this is like knowing some very basic, it's like calculus, right? What is the derivative of x square, log x and so on. Similarly, you need to know what is the Bernoulli, what is the categorical, what is the multinomial and so on. But I'll describe when I use them. So here I'm only using Bernoullis because I want to kind of show you why doing maximum likelihood here is kind of directly hard, and therefore we are going to motivate EM method to kind of fit the parameters. So what are the parameters here? You can just eyeball, right? The parameter is going to be mu1, sigma 1 square, mu2, sigma 2 square, and pi. there are 5 parameters in this model. Okay. Just like in the simplest fitting one Gaussian, you had 2 parameters, mu and sigma square. Here you have 5 parameters. Okay. Yeah, so Gaussian mixture models, okay, just why did I bring this up? As I said, it's extendable to k Gaussians and multiple dimensions as well. This is a one-dimensional Gaussian that I'm thinking of. And Gaussian mixture models were the predominant component in speech recognition, actually. So before all this deep learning stuff came about, which is past, let's say 5 years. Before that, I don't know how many of you have heard of this software called Dragon Naturally Speaking, advanced software. So there used to be the software vendors who used to sell speech recognition software, which you can install and actually just say something to your computer and it will type it, right? Same thing with modern systems like Cortana, Siri, or any of these other things. So a predominant component there of how to kind of model, like when you say something, it's going to be voice and it has to be translated into text. So to go from voice to text, they had to build a model which would say, given text, how would the voice sound like? Okay. It's like base rule type of a thing where you want to go from voice to text, but in between you want to actually have a model of how does voice sound like given text. Okay, so that they will use to model as a Gaussian mixture model. Okay. And that's not just a unique case. I mean, Gaussian mixture models are useful for any sort of unsupervised learning as well. So if you have data, you can't always visualize this. In 1 dimension, maybe you can just draw histograms. In 2 dimension also, you can just plot it, put it on your, it's like a scatter plot and see if there are like bumps or something. But in high dimensions, you can't do that. But you can always assume that maybe a Gaussian mixture model fits the data, fit a Gaussian mixture model, and then kind of, it's related to things like clustering and so on, which we'll see later. Okay, and maybe you've seen this in 572. Okay. That was a tangent. Let's come back to, okay, so given this description of, this is a model description of how what is random variable y, and we have seen realizations of random variable y. Okay. So if you actually write the density function, which I want to write it as, so p of y, density function of y is actually going to be equal to just simply 1 minus pi. What should I write? P of y1 plus pi p of y2. So what is this notation? So when I write p of y, I'm just p of y is actually just probability of y taking a value little y. Okay, and similarly p of y subscript 1 is saying P of y subscript 1 is actually just the normal distribution, which is exactly P of y1 is just y1 taking a value little y, and so on, right? P of y2 is just y2 taking a value little y. So I'm just using a short form to say that it turns out that the density function of y happens to be related to the density function that we know of the other random variables. Just like y is equal to 1 minus delta times y1 plus delta times y2. Turns out that the density function of y, that the random variable y takes a value little y, is just 1 minus pi times the probability that y1 takes a value little y, and plus pi times the value probability that y2 takes a value little y. It turns out that this is the case. Okay. And now if you think of doing maximum likelihood estimation, okay, okay, let me actually explicitly write this, 1 minus pi plus pi. Let's ignore this whole thing. Okay, so what I'm saying is this is what we wanted. This is the probability of the variable that corresponds to data that we have, y1 to yn, y1 to yn, and it's related in this way. Then and there are also parameters which I could explicitly write. So let me write it here. Maybe p of y of capital Y is equal to y given the 5 parameters. Let me just vectorize them, as in just write it as there's a pi, there's a mu1, mu2, sigma 1 square, sigma 2 square. Okay. Those are the parameters. This is like as explicit as you can write it, right? And you can see that there's a pi here, there's a, within these is going to be sigma 1 and sigma 1 square and mu1, right? Because this is just this, I can expand this, but I think it's not a good use of time. This is just the normal distribution, okay, at y1, at y is equal, so at y1 is equal to y. Now, now if you think of MLE, then all you need to do is take the log of p of y is equal to yi. Let's say you have y1 to little y1 to little yn as your data, okay. You just have to do this, right? Sum over I is equal to 1 to n. This thing, which also, you know, depends on theta. So I'm just going to call this as theta, okay, for simplicity. So theta is not, you know, is just a symbol for this vector, and I just need to maximize over theta. Okay, that's the MLE problem, and you can see that because this is the sum of two normal distributions, like you know, sum of, you know, it's basically 1 minus pi times some factor times e to the power y minus mu1 square divided by sigma 1 square. That would be the first term here, right? And then plus pi, and there will be another factor, basically 1 by square root 2 pi sigma 2 times e to the power, you know, y minus mu 2 square divided by sigma 2 square. That would be this term, right? If you just substitute it naively, it's not clear how to maximize this problem, okay? That's the kind of key observation that you need to make, that if you had one Gaussian, log and exponent kind of cancels and you have like a square objective, okay, where you can easily take a derivative with respect to mu1 and see that mu1 is just the average of the observations. But since we have two Gaussians, log cannot be, and there's an addition here, you cannot just take, basically it's the sum of two exponential functions. So you cannot cancel log with exponents, okay. So that, what I'm trying to motivate is that this term looks messy. So there's a log, there's an exponent, plus another exponent, okay. Taking the data, and now you have 5 variables actually, it's a 5-dimensional optimization problem. In a sense, you need to set 5 good parameters, right? So doing this even computationally, so forget about doing it, getting closed form expression for these 5 parameters. Even doing this computationally is messy, in the sense. So this is the first time I think we're talking about computation. Actually, if you remember logistic regression, there was no closed form expression for beta, right? So you had to do some computation, which we kind of ignored. Even for lasso, there was no closed form expression for beta, right? There was some computation that we had to do. We kind of ignored that computation aspect. Here is the first time I'm talking about computation. I'm saying that this is a messy objective that you want to maximize over your parameters, theta. So, which means that you want to, you know, first of all, there's no closed form expression, like, you know, residual sum of squares type of thing. There's no closed form expression, just means that there is no simple way to say theta hat is a function of data, which is y1 to yn, right? There is no, okay, let me not use it. So, theta hat is not a simple function of data, okay? So you have to use some computational technique to figure out what theta hat is, best theta is, okay? Just like you would do with lasso, just like you would do with logistic regression, okay? Now, even computation is messy because there is no unique theta. Even computation is messy because it turns out this maximizing over theta of this function, okay. If you just think of theta is not one-dimensional, it's 5-dimensional. But if you think of x-axis as theta, let's say this is a function, it has some surface like this, okay. It has a lot of local maxima, So because it has lot of local maxima, it's kind of hard to. That's when I call the problem a messy optimization problem. Okay. This is not the case for logistic regression though. For logistic regression, although we have to do computation, it turns out that for logistic regression, you would have whatever there's going to be beta there. For logistic regression, you'll have a maximizing. The objective turns out to be like a nice one where there's only one maxima, or actually in logistic regression you're minimizing some score, cross entropy loss, I guess. Yeah, there's some minima. I think I drew this picture when talking about logistic regression. So this is still computational but nice. This is computational but messy. Okay, that's what I mean. Okay. So that leads to a different technique, which is gonna still handle this messy problem, but in a relatively nice way. Okay? Because this is the problem that we have to solve. We have to find theta that best maximizes the likelihood. It just turns out to be a messy problem. So what do? Even computationally. So we're gonna do something interesting, which is this EM method. Okay. So for that, let's say we have these data points y1 to yn. And I'm gonna now hallucinate, or again conjure that I have observations delta 1 to delta n. Okay, so I'm gonna say that maybe I know these realizations of the Bernoulli random variable. If you remember, our model was first you flip a coin, it may land on heads or tails. That you don't observe anyway. We only observe y's, right? Which would turn out to be like a 2 Gaussian type thing if you drew the histogram. But here, let's say we observed the outcome of this head and tails thing. Okay, that's these realizations. I'm going to call them little deltas to kind of differentiate from the capital delta I use for the random variable, right? And if that is the case, then let's say I observe these, then what is the probability of y taking a value little y and delta taking a value delta? Okay, I'm gonna try to find this. So it's the same random variable and same delta from before. Y was this sum of 1 minus delta times y1 plus delta times y2, right? And delta took a value little delta. It turns out that this probability is equal to 1 minus pi times the probability of y1 taking a value little y to the power 1 minus delta times pi times probability of y2 random variable taking a value little y to the power delta. Okay. No, pi is the bias of a coin. Remember at the beginning I said there's this delta random variable which has this bias, coin bias. Think of pi as a 0.5. I mean, pi can take values between 0 and 1. It's a parameter of a Bernoulli distribution. Right? This is the pi here. So these are all the parameters. Mean, variance, mean, variance.
No, no. Because you said the node takes value of 0 or 1.
This takes value 0 or 1.
Okay, not pi.
No, yeah, pi can also take value 0 or 1. If it does, then it's a very degenerate parameter. If it takes a value 0, then you're always getting tails. Okay. So this is like the bias of the coin. There has to be some bias.
Is that number for us going to be like 5 or?
Yeah. Yeah, pi is 0.5, then it's a fair coin. Have you seen Bernoulli distributions before in 570, let's say? No? 570 was statistics, right? But I mean, you have to look at some, you're looking at statistics of something, which means that you're talking about some distribution, either a normal distribution or Bernoulli or something, right? Okay. So how did I write this? So let's try to understand why this is true. Okay, let's say delta is actually so delta is a random variable. It takes values, right? That I'm saying let the value that it took be heads or tails. I'm just representing it as a little delta. It could be 0 or 1. Okay. Now this formula is the right hand side seems unwieldy, but it's like a nice way of writing this joint distribution between y taking a value little y and delta taking a value little delta. It's basically saying if delta is equal to 0, okay, then this is second term to the power 0. So something to the power 0 is always 1. Okay, that's convention used in math. And so second term is gone. And it's saying that if delta is actually equal to 0, then the probability that y is equal to y, little y is just 1 minus pi times y1 taking a value little y. And the other case is symmetric. Okay. So try to kind of see. So this I'm looking at a joint distribution of two random variables. Okay, taking two values, two fixed values. Previously, we were looking at the probability of y taking a value little y only. Okay, so that's why there was a summation term previously. Here there is no summation term. There is actually a multiplication. Okay. Now, if you try to maximize the likelihood of this, then you're fine because log and exponents kind of play nicely. Okay. So and even here there's an exponent. So multiplications and logs also play nicely. So log of a times b is log of a plus log of b, right? So if only you had this data, this coin data, whether it was heads or tails, if you could observe that as well, then you would maximize likelihood. So this is depends on theta. Theta is that 5-dimensional vector with pi's and mu1s, mu2s, sigma 1 square, sigma 2 square, right? You could maximize if you observe both, then you would maximize this term on the left side. Okay, maximize the log of the left side would be the likelihood term. Okay, because you observed both both y comma delta pairs. Okay, so if you had this data, then you would maximize likelihood nicely because log and at least exponents play nicely. And it also turns out that if you had observed both, then for example pi, for example, estimate of pi hat would be just 1 by n times sum over I is equal to 1 to n of delta I. It's just going to be like pi is just the bias of the coin, right? So if I had observed 3 heads out of 10 trials, then my estimate for the bias would be 3 by 10, right? So it turns out that for this problem, you can, if you had observed the second data, you would get closed form expressions of each of the parameters. Okay. Is that, who's lost at this point? What's happening? I'm saying that if you had this additional data, if you had observed, we are in a hypothetical situation where if I had observed the outcomes of the deltas, then this would be my likelihood, likelihood function, and take the log of this. And log is nice because, even if there are only multiplications here, so log is fine. It turns out that if you maximize over theta of the log likelihood, take the log of the left hand side, you will actually get the theta. For example, let's say the first coordinate of theta is pi, and pi would be a simple function of the observations. Similarly, mu, let's say mu1 hat would be, essentially pick the data which corresponds to tails. There will be some yi's which correspond to tails. Take the average. Basically take average of yi's where delta i's are 0 or tails. So you'll have some nice closed form expression. So you really, it's not even a computational problem anymore if you had observed the second data. Okay. So what EM is going to do, or given with this example, that the moment you observed second data, which was this deltas, realizations of the coin tosses, the problem became easy. It's not even computational anymore. It's actually closed form. You get closed form expressions. Okay. So with that, I guess insight, we're going to design a algorithm. Okay. Algorithm which will have which will do, okay, I just say algorithm just means a sequence of steps. Okay, it's a procedure. Okay, step 1, step 2, step 3, step 4, do something which tries to estimate delta i's and then estimate theta given yi's are anyway given always, given yi's, and now estimated delta i's, right? I estimate theta given yi's and delta i's. That is easy. And how do we estimate delta i's? It's going to say, let me estimate delta i's given theta. Okay, given yi's and theta. Okay, it's basically saying, okay, what do I know? Let's say yi's are anyway given. That's my data. I can always use it. The algorithm is going to say, if I could have filled the data, this missing data, this delta realizations, if I could have filled it, the problem is easy. So at least the second step, if I could know what the deltas were, the problem is easy. I can estimate the parameters. But I don't know how to fill the delta. So let me come up with a way to fill the deltas. I'm going to estimate, I'm going to somehow come up with some estimates of delta given what I know so far, which is just the data itself. But maybe I can also just put a candidate thetas that I know. Okay. So the way I've described, there's some dependency, right? I mean, I want to estimate theta, but I need theta to estimate delta. So, and I need delta to estimate theta. So there's some dependency in both steps. So a very natural way to resolve this is to say is going to be the algorithm, which is start with any theta, let's say theta naught. Okay, estimate delta i's, okay, given yi's and theta naught. Okay, so this step I'll in fact, what is that estimate going to be? It's going to be just the expectation each delta I. Okay, instead of so the estimate of delta I, I'm going to call it gamma I. It's going to be the expectation of the delta random variable given data yi, comma theta. Okay. And then given, so now I know gamma is. So okay, I said estimate delta i's. Delta I is supposed to be either zeros or ones. Okay. Instead of estimating delta i's, I'm going to estimate a number which is going to be between 0 and 1. So let's say there's a random variable delta I corresponding to little delta I. Just to kind of not confuse you with this, it's not like there's a single delta. There's many different capital delta random variables, right? One for each yi. So I'm saying that, let's say I start with some parameter theta naught. Okay, that's telling me, that's basically telling me what pi is, what mu1 is, what mu2 is, sigma1 square is, sigma2 square is, basically. If I know that, and I know the data, it's always given, I can find the probability, I can find the expected value of this random variable delta I. Okay, since delta I is a Bernoulli random variable, it turns out that its expectation is always going to be between 0 and 1. If it's Bernoulli random variable taking two values 0 and 1, then its expectation is going to be between 0 and 1. Okay, so I'm just calling it gamma I. Okay, I mean I could have called it delta I, but I've chosen delta I to be actual realizations of capital delta I, which only can take values 0 and 1, 0 or 1. Okay? Cannot take values in between. So instead of estimating delta I, I'm saying I'm going to estimate some other quantity, which is like a soft thing, right? If delta I was 1, if I can estimate, if the expected value of delta I given my parameters and the observation data, maybe it's 0.9. Okay, can happen. So estimate gamma i's. Then now I know gamma i's. I'm going to now estimate theta 1, which is the next set of parameters given data yi, and now my estimated things, which is going to be gamma i's. Okay, what are gamma i's? I'll just plug the gamma i's wherever I had deltas. Okay, so you saw this expression, right? P of probability of the likelihood term has something which involves deltas. I'm just going to replace deltas with gammas. That's all. Okay. So I'm going to estimate theta 1. Okay. And then I'm going to again estimate, let me call it just gamma i's given yi, comma theta 1, and keep continuing. So what I'm saying is I had this deadlock. So the intuition was if I could know deltas, I would have an easy problem, but I don't know deltas. So I'm going to start with some estimate of my parameters. Given the estimate of parameters, I'm going to, given some parameters, starting parameter, I would say what could be the possible values of these unknown random variables. Okay. Instead of deltas, I'm just calling them gammas because these are not actually, these are numbers between 0 and 1. Okay. And if I know gammas and y's, then I can estimate theta. That's what we saw earlier. Okay. And the thing is, you start from any theta naught. Given theta naught, you're estimating gammas. With data and gammas, you're estimating a new theta. Then use the theta, estimate new gammas. Use the gammas and estimate theta, and so on. Okay, so basically it's a for loop. Yeah.
And just so the gammas are estimates for the little deltas.
Yeah, gammas are estimates for little deltas take value 0 or 1, which is the realization of the corresponding random variable delta I. It's just that you don't know, what value it took. So you're just saying what is the expected value it took. The intuition is, ideally I want to know what exactly this random variable took, whether it took the value 0 or 1. And if I knew that, then you saw that the problem is easy, right? The likelihood function has a nice form. But I don't know I don't know how to exactly estimate whether the random variable took exactly value 0, was tails or heads. I just want to know in expectation what value it took. And in expectation kind of fuzzies it out, right? It's going to be a number between 0 or 1. And that's why I'm just calling it gammas now, to confuse with the deltas. But the idea is still the same. Gammas are just going to replace deltas wherever in the likelihood function that I wrote, like before. So this is the EM algorithm. It looks very ad hoc, right? Right now it's a 2 Gaussian mixture model, and we said MLE problem is hard, but if you had full data, the problem is easy. So we are just filling the data. So EM is all about what is that we don't know. We don't know what some random variables that we did not observe. We're going to fill in some values for those random variables, generally they're expected values, And why is there a given part? Because you just don't want to randomly fill the numbers. I mean, you want to fill the numbers given all the information you know so far. All the information you know so far is the data itself and what is my current estimate of the path. That's why I put these things here. Okay. Fill in some numbers, fill in the missing numbers, and if you fill in the missing numbers, estimating the parameter is going to be easy. So EM is all about filling in some numbers for your model, and once you fill in the numbers, the problem is generally easy. Maybe it's computationally easy, maybe not closed form. I mean, here we have closed form, but in general it will be easy.
That's why they put given the text, how the voice would
That they would model it as a mixture of Gaussians. Yeah, it's like here we are looking at a mixture of two Gaussians in one dimension. There they would have a mixture of k Gaussians in d dimensions, where d is like 10 or 20.
The estimate of theta 1 would be how they given the text, how the voice would impact.
No, I mean, so after all this you get some theta vector, right? In two Gaussian mixture case, it's the mean and the variance. Mean 1, mean 2, variance 1, variance 2, pi. For that k Gaussian mixture case, there's going to be pi 1, pi 2, pi 3, pi k minus 1, things like that. Mean 1, mean 2, mean 3, mean k. Covariance matrix 1, covariance matrix 2, covariance matrix 3. So it's a bigger problem. But once you estimate the thetas, then it turns out that the probability of acoustic signal given text that they can represent. So what we are estimating here is a distribution of multiple Gaussian mixtures, right? So there, the conditional probability of a voice given text is modeled as a Gaussian mixture itself. Okay, that's it. There's no, don't try to think what was the text part. There's no text part here corresponding to your intuition to that side. Yeah.
How do we know to stop? Is it stops changing?
Yeah. So this is an algorithm where you keep running in for loop. It has to stop changing, and next we'll see why it makes why does it work. So what it will do is actually. So first of all, the problem is messy. You have to find theta. Okay. So what we have done is just hallucinate some new numbers to make the problem easy and describe a computational procedure. Okay. The computational procedure, what it's going to do is start from some theta value. Okay. Maybe let's say some theta value here. We start from some theta. The computation procedure is going to make you're getting theta naught, theta 1, theta 2, theta whatever, t iteration. That's going to let you climb up the hill here. This is, let's say here. It will let you at least get to this theta. That's what the computation procedure will do. That's what EM will do. EM will let you climb up in the original data likelihood objective function. Although EM is doing something else, right? It's hallucinating about data and doing some other optimization. The original optimization that you're supposed to solve is that messy one, right? The messy one had this, I'm calling it messy because it has something like this. Okay. EM procedure will still, whatever iterates you get, turns out that those iterates means the theta 1, theta 2, theta 3 values, they let you, if you evaluate them, you will see that the data likelihood, the original probability of y, log probability of y only, that will increase and stop at some point.
Do you find just one maximum, or do you find?
You just find one. I mean, if you start with some other theta naught, maybe you'll find something else. Is that fine? How much time do we have? Okay, we have 8 minutes before maybe a break, and I wanted to see if I can motivate. So in the notes there is actually an algorithm in figure 3, but it actually explicitly gives you the formulas for, I said, where is this? It explicitly gives you what this gamma I is. It explicitly gives you what this theta is, okay, in the notes. But let's not worry about that. It turns out that if you actually compute the expectation of delta I given data and theta naught, it turns out to be some closed form expression. Okay, that's not. I mean, I can derive it if somebody I mean, you try to understand what it is first. If you understand the template, then you can easily understand what the formulas are. Okay. So I'm just trying to see. I wanted to show why EM works. As in, so I just made a random claim, right? The claim was, I just made a claim that if you do EM, you're working with some other likelihood, the joint likelihood of data, observed data and some hallucinated data, right? That's what you're trying to maximize or something, in between at least. If you do EM, you will also increase. So EM is an iterative algorithm. It's step by step giving you some. It's giving you theta 1, theta 2, theta naught, theta 1, theta 2, and so on. It will also you will also increase the likelihood. L of likelihood of data. There is L of what's the likelihood? So let's say log of probability of y is equal to little yi. Yeah. So this is the likelihood, right? See, in EM we were not really touching this object because this was messy. In EM we were doing something else. But the claim is that if you do EM, you will also increase this likelihood term. I only said increase because we will not reach the actual maximum, because it's first of all the maximum. There are many local maxima in that problem. We can't say which one to get to, but we will increase. Okay. There is an explanation for that. I was thinking, do we have time? Okay, I think we have time, so let's actually understand why EM works. Okay. So intuitively, so there's a claim, and let's see why the claim is true. Okay. Why is this true? Yeah, if you don't understand my handwriting, definitely ask. So in the notes I use so in general, so I was using y's and deltas as observed and unobserved, right? Deltas were unobserved, Bernoulli flips, and y's were observed, right? So in general, I'm going to say z is observed and zm is unobserved. Okay, so z is some random variable. It could be one random variable. It could be like random vector, like it could have multiple components. And zm would be another set of random variables which I don't observe. Okay, and there could be some relationship between, how did z's realize? There could be some way you're describing that, something happened, some coins flipped somewhere. Ultimately, z got realized. Okay, there could be some relationship like that. Okay, so I'm gonna call this together. I'm going to call this to all the random variables t. Okay, so it's just a general picture, the more abstracted picture where I'm saying if you're not comfortable, you can just think of z as y and cm as delta. Okay. Then the probability of z given some parameter. Let me call it theta prime here. Just to I want to use theta prime here for some parameter theta prime. Okay, this is the likelihood of the data under the model theta prime. Okay, is equal to probability of t given theta prime divided by the probability of zm given z given theta prime. You don't have to focus on copying this, try to understand what's happening. So can anyone kind of, given that you have spent some time, is this like a complicated formula or is this okay? Huh? This is just factorization of a distribution. So probability of t is, think of probability of t as this joint distribution. Probability of t is a joint distribution. So basically all I'm saying is probability of, let's say, xy I don't want to use x and y. Let's say uv is probability of u times probability of u, probability of v given u, right? This is known. Oh, my v's are looking like u's, so I just took this second guy in the denominator. That's all I did. Okay, and now I want to say, so take the log on both sides, log. Then the left hand side is actually the log likelihood that we care about, L of data given a parameter theta. That's the log likelihood of the data given a fixed parameter theta theta prime. This is equal to something else, which is I'm going to call it L0, which is the log likelihood of the full data, with the hallucinated ZMs potentially at parameter theta prime, minus this additional term. I'm going to call it L1. It's going to be probability of ZM given Z and theta 1. So all I did is change some notation. All I'm saying is there was a ratio. I took log on both sides. Log of A divided by B is log of A minus log of B. So that's what this is. Okay. This is what we care about. We want to maximize this, right? This was a problem which was messy. Probability of data given parameters. EM is actually maximizing in the M step. Okay, I didn't say which step is what. Let me go back here. This, because there's an expectation involved, you can think of this as expect E step or the expectation step. And because there's a maximization involved, because you are trying to estimate theta given complete data. That's some other maximum likelihood problem. This is called M step. Okay. So E step is taking some expectation. So it's taking the expectation of unobserved data given everything else, current estimate of theta and my data. That's why it's called E step. In M step, we are saying I've hallucinated about the data now, which is gammas. I'm taking the gammas now, and I have the data, and I'm going to now maximize this joint likelihood of real data and the hallucinated data that I have. Okay. So it's some other likelihood problem which I'm maximizing. So it's the M step. Okay. So EM is actually doing, at least in the M step, is actually maximizing this. What we want to maximize is this. What we want to maximize is this. EM is only maximizing at least this guy. Then there's this additional term which we are kind of deleting essentially, right? And a claim is that EM is doing something. It's not just doing M step; it's also doing E step and so on. It's an iterative algorithm, but it'll also eventually also maximize. Not eventually. Every time it's also maximizing the original data likelihood as well. That is the claim. Even though EM is only touching this guy in terms of maximizing, EM is also maximizing this guy. Okay, that's the claim at least, right? To see that,
what's in the parentheses in the first one? Want.
okay, want. Yeah, this is want. So this is M step of EM. Want to maximize. This is want to maximize. I mean, this is the data likelihood. Okay. EM is hallucinating some random variables and doing some other maximization. Okay. So what we're going to do is actually to reason why EM makes sense. We're going to look at on the left side. We're going to take an expectation with respect to unknown data given known data at some point at some parameter theta. Okay. So what do I mean by that? You see, this is a function of full data given parameter theta prime. Okay. This is a function of unknown data given real data and theta prime. Right. I'm going to take a expectation. Let's write this. expectation with respect to what is L naught, depends on full data and theta prime, with respect to the hidden okay, let me explicitly write this so that it's kind of very obvious what I'm doing. All this notation is not useful, so let's see. Let me just do a sum of p of zm given z comma theta. That's what I'm saying. I'm gonna take an expectation. So this is some term, right? This is a function of random variable, right? So I can take some expectation with respect to it. So I'm gonna say take the expectation of this guy with respect to a conditional distribution. T also includes Zm, so you can average over Zm. So I'm gonna do sum over Zm of a probability, which is a conditional probability of Zm given Z, times the first term. Okay, but kind of very important, this is just theta, not theta prime. Okay, and I need to take an expectation with respect to the second term, which is also same thing, sum over Zm of p of Zm given Z comma theta times L1 of Zm given Z comma theta prime. Okay. I took an expectation with respect to some distribution, okay, because there are random variables involved in both terms. This involves Zm, this also involves Zm and Z. Okay. If I take it, so, but the key thing is I took an expectation with respect to some other parameter. That I can always do. I can say T is distributed according to one distribution, I can say T is distributed to some other distribution. I can always say that. Okay. So I took an expectation on the right hand side of this term and this term with respect to some distribution. I should also take an expectation with respect to the left hand side. But on the left hand side, this is not a random variable. Zm is not a random variable on the left hand side. So there's no point taking an expectation. You can take the expectation, it just cancels out. Comes up to 1. Okay. So if you had this term here, then the summation just is equal to 1, and so it doesn't matter. So left hand side remains the same. All I'm saying is right hand side, these expectations cannot be removed because T involves Zm, so it's a function here, and here also Zm and Zm, so you can't really remove. Okay. But I added these expectations, and actually this so this is actually, I'm going to call it Q of theta prime comma theta, and this term I'm going to call it as R of theta prime comma theta. It's just two functions. This actually there's a theta and a theta prime, there's a theta and a theta prime, so I'm just calling it, this is a function of, there's some function of theta and theta prime, there is some function of theta and theta prime. Here I said this is the M step. Actually this is not entirely accurate. M step is actually maximizing this guy, this Q function. Okay. So in EM what's happening is, so this was just a definition of conditional probability and taking logs. Left hand side is what we are interested in. Right hand side, there are two terms. I took an expectation of the whole equation with respect to a particular conditional distribution. Okay, and I'm saying that this is the term that EM maximizes in the M step. And why is that? You remember this? This is essentially saying I have data. Z is the data. Theta is the parameter. I'm gonna kind of estimate what is the, I want to hallucinate what are the different values that Zm can take, the unseen data, right? In the two Gaussian mixture case, this was actually just gamma I. It was the probability, there it was the expectation of delta given my data and the current parameter theta, okay? And the gamma is being substituted in the next M step, right? So this is the equivalent of that gamma. once you substitute this, and it turns out in the Bernoulli case, it's gamma and 1 minus gamma, right? There's a summation over two things, okay? And that's what you'll see if you remember, if you look at the complete data likelihood, okay? So what I'm saying is, previous estimate, let's say this is theta naught. Given theta naught in data, you estimate something, that is this thing, gamma. You plug the gamma in the second term, in the complete data likelihood, and then you maximize over theta prime. Okay? That's what's happening in EM in the previous case. And so this whole thing, I'm calling it is Q, and this is what is being maximized over theta prime in the M step. Is that at least intuitively clear, or is there some confusion? This is what is being maximized in M step. And what is being done in the E step? E step is just computing the probability of Zm given Z comma theta. That happened to be gamma I in the previous case. Although gamma I wrote it as expectation, is actually if you want me, I can go back there. Where is it? I wrote it as an expectation, but delta is a random variable which is Bernoulli. So expectation of a Bernoulli random variable is also the probability that the random variable is equal to 1. Okay, I could have written it as P of the hidden thing equal to 1 given data, given Z comma some theta, right? So what I'm saying is this gamma is an example of this guy. E step, whatever the current, you start with some parameter, right? So whatever the current parameter is and current data is, this is the data, this is the parameter. Tell me what could be the probabilities of the missing data. So I'm using M to kind of talk about missing data. This is data that is not there, that's not given to you, so it's missing. Okay. In E step you compute this, and in F step you actually have to use it, right? So the way you're going to use it is actually just plug that in as multipliers for the total data likelihood. Okay, that's what's happening even in the previous case. So this is the M step. So why I'm introducing all this notation is to kind of come back to the claim. The claim was that we had this original data likelihood that is messy, but EM is actually also maximizing the original data likelihood. Okay. Now that we have set up, we have just used some very simple algebra to kind of set up that EM is actually just at least maximizing the first term of something related to the data likelihood, right? This was the data likelihood. EM is at least maximizing the first term. Data likelihood decomposes into Q minus R. EM is maximizing the first term, at least in one of the steps, but it's not touching the second term anyway, and the second term doesn't come into the picture. How is it that it's making progress? Okay, progress means that it's actually every theta iterate is actually increasing the data likelihood, the thing on the left side. Okay, and the way to reason about that is say the following. Let's say I have theta. I went to theta prime. Okay, let's say my previous iterate value was theta, and I did the M step. I got theta prime. Okay, which means that Q of theta prime comma theta was maximized at theta prime. The Q is the function that is EM step. M step is M step of the EM. So let's say it was maximized at actually theta prime. Okay, some number. This is the previous iterate. This is the current iterate. Okay, that means that Q of theta prime comma theta okay, let me not write this. So I wanna say we are increasing the data likelihood. So what I want to say is actually that L of data given theta prime, which is the next iterate. So next iterate, my iterate value, my parameter estimate is theta prime, minus L of Z given the previous iterate theta. That's the improvement, right? That's the two numbers successive set of parameters. I want to show that this is actually greater than 0. That means that I'm climbing the hill, right? I'm saying previous iteration I had some estimated parameter theta. I did some EM step. I got some new parameter. In the M step, I actually maximized something. I got some theta prime. In fact, I maximized this. Let's say that was maximized theta prime. So I got some theta prime. I'm just substituting that in the likelihood. With this parameter, there's some likelihood of data. With this parameter, there's some likelihood of data. I want to say that by when I say I'm making progress, I want to say that the new estimate, the new parameter, the likelihood is greater than the likelihood at old parameter. This is what I want to show. Okay. And this I can show by saying that because we know that these L's, which were the left hand side of the previous equation, were just q of theta prime comma theta minus this would be just q of theta comma theta minus r of theta prime comma theta minus r of theta comma theta. Do you agree? I just substituted what L was. L was this minus this, and what is L of at theta itself would be q of this minus this. Okay. And there's a minus sign there, so minus q and minus this plus r. Okay. It's a little seems like laborious, but I'm just trying to justify why EM works in general. Okay. And at this point, I want to say that since q was maximized at theta prime, okay, this is a function of theta prime. This is maximized at theta prime. That means that this is going to be greater than any other value that's substituted in the first argument. Right? Because q function, we are maximizing over the first argument, and theta prime was the point where q was maximized. So for any other value of the first argument, this guy has to be greater than this guy. Right? So at least the first term is positive. That's what I'm saying. We wanted to show that this difference is positive. The first term is positive. The only thing that remains is to say that this term is negative. This term inside is negative, then the negative, positive. So both terms are positive means this difference is positive. That's roughly where we're trying to get it. Okay. And the first term is positive by definition of, we're maximizing q over the first argument in the m step, so of course the first term is going to be positive. First difference, is going to be positive. All that's left is to show that, or to show that the whole second term, including the negative, is also positive. So basically, what's left is to show that minus of so what was r? R of theta prime comma theta was actually sum over p of zm given z comma theta times log of p of zm given z of theta prime. Okay, that was what r was. Remember, r had this. First of all, the L1 term, the second term was essentially this, and I said I'm going to sum over a conditional distribution over Zm. Sum is over Zm. Okay. This was R of theta prime comma theta. I wanna show. So let me just make some simple substitutions. Let's just call this let's just call this Qi. And let's just call this Ri. Okay. Simple. I mean, we don't want to kind of confuse like what is all this conditional stuff going on. Let's just say there are two different conditional distributions. One has something to do with theta prime. One has something to do with theta. They are on the same domain or same support of the random variable, right? So let's just call this Qi and Ri. And let's say our function is just sum over I of Qi log Ri. Okay. Essentially, that's what it is. Two different distributions. Okay. You're summing over Zm, the hidden variable, or the missing variable. Maybe it takes some values, let's say 3 values, and sum over I is equal to 1 to 3. All I'm saying is there are two distributions, qi log ri. That's your R function, right? So what am I left to show? I need to show that the negative of sum over qi log ri, sum over I, minus r theta comma theta is going to be sum over I qi log qi. This thing is greater than 0. That's all I need to show. I just made some change of notation so that we don't kind of get confused with this heavy notation. Is this change of notation fine? We are exceeding the time for taking a break, but let's finish this and then take a break. Is the notation fine? All I said is this is some distribution, depends on theta. This is almost the same thing except it depends on theta prime. So I'm going to call it two different distributions. I'm just saying this was the definition of R, theta prime comma theta. So I'm gonna, the one involving theta, I'm gonna call it Q. The one involving theta prime, I'm gonna call it R. And the R function is just this. Okay. Essentially, the theta prime guy is here, theta guy is here. Okay. And this R theta comma theta is just, there's no confusion. This is Q comma Q. That is QI log QI. Okay. Yeah, I'm tacking on the minus with me, so that's why I showed these two is positive. This whole thing I'm saying is positive, or you can say the one inside bracket is negative. The same thing. If I can show this is positive and this whole thing is positive, then the left hand side is always positive. No, I have put a minus here, so you can say yeah, I can remove the minus and say this is less than 0. Same thing. Right. In fact, what you said, I'm going to do that, and in fact, I'm going to also simplify because they have the same coefficients, and maybe there's a log of a minus log of b. So let me just merge them together. So sum of qi log of ri divided by qi. Right. I want to show that this is less than 0. Right. And how do I, so the thing that I am varying is theta, so Ri corresponds to theta prime, right? That's the thing that that's the one which got varied, okay? In the end step, that's the one I'm changing. I'm saying I'm going to pick theta 1, which maximizes the first term, q, so theta 1 was one changed. So if I keep changing Ri, I'm saying that fixed Qi, I change Ri, that's never gonna, whatever Ri I pick, this is always gonna be true. That's what I'm trying to claim. In general, I can say that, okay, let's say maximization over Ri is always, this is saying whatever value of Ri's you pick, you're never gonna exceed 0. Okay. That's fine. Okay. And this seems like a tackleable problem in the sense, okay, how do I show that the maximum of this thing is never positive? The way to show it is to just take differentiate, take first derivative and set it equal to 0. Okay. But with one interesting thing which I did not write, sum of Ri is equal to 1. These are all distributions, right? There was a conditional distribution here. There's a conditional distribution here. So sum of qi is actually equal to 1 and sum of Ri is also equal to 1. Okay, that I need to remember. It's an important constraint actually. Okay. So I don't know if you remember how to maximize a function with a constraint, but it's just amounts to using what is it called? Lagrangian, I think. But anyway, I'll actually do it here. So sum of qi. So I want to take the derivative with respect to ri. Sum of qi log ri by qi minus or plus, doesn't matter. Minus lambda times 1 minus sum over i. equal to 0. If you have a constraint, what I'm saying is you'll have a Lagrange multiplier, okay, which multiplies the constraint. Okay, if sum of Ri is exactly equal to 1, then this term is 0, right? So what you do is you take the derivative with respect to Ri, you take the derivative with respect to Lagrange multiplier, and set them both to be equal to 0. Actually, if you set this equal to 0, you actually get 1 is equal to sum of Ri, right? Because lambda is only there, so you take the derivative of this thing. This thing is called the Lagrangian. Let me use lag. Okay. The Lagrangian. Take the derivative with respect to variables that you want to optimize for. Take the derivative with respect to the Lagrange coefficient. Okay. It's called lambda is called Lagrange multiplier. So let's take this derivative. So Ri is only appearing in one of the terms. So let's say this is Qi log. What is the derivative of Ri? It's divided by Ri, right? And there's a constant. So Qi log Qi, that's that comes as an additive term, so that gets cancelled. Minus lambda times Ri is equal to 0. Oh no, lambda times 1. So why is this true? If you think of, forget about the denominator, because there's basically it's Qi log Ri minus Qi log Qi. Qi log Qi doesn't have Ri, so that's a constant. Take the derivative of this guy with respect to Ri, you get Qi divided by Ri, right? Log of x derivative is 1 by x. Now there's only one other Ri in the second term. Take the minus lambda, which is just a coefficient. You take the derivative of this with respect to Ri, you get, I guess, minus 1, right? So actually just put plus 1. Okay. Actually, yeah, it doesn't matter. So we have this. It implies that Qi by Ri is actually equal to minus lambda, which means that all the ratios are equal. All the ratio of Qi with respect to lambda is equal to something. Okay. But we know that they need to sum to 1. The individual ones sum to 1. Okay. We also know that sum of Qi is also equal to 1. Okay. We know that from before. It's Q's are district PMFs, right? This basically implies that Ri is actually equal to Qi at the maximum. If the ratios are constant, they all sum to 1. Okay. Both sum of Ri is 1, sum of Qi is 1, and the ratios are constant. Okay. Then Qi is equal to Ri. I mean, you can just see that, right? Qi is equal to minus lambda times Ri. Sum over the left side, that's 1. Sum over the right side, that should also be equal to 1. What I'm saying is lambda is minus 1. In other words, if you want to play with this, all I'm saying is lambda is minus 1. This is the first derivative. We set it equal to 0. Got this. If you just substitute this in here, when Ri is equal to Qi, what is the value of this term? 0. So the maximum, whatever theta prime I pick, the maximum value that this guy can take is always less than 0. Or maximum value is 0. That's what we wanted to show. Maximum value is 0, or the negative is always positive. So this term is always positive is what we showed. So that's what we showed. We showed that EM improves data likelihood in every iteration. Okay. So it will do the hill climb. Just coming back to this simple picture. Start from wherever. So that's arbitrary. Start from wherever. Start from here. It will do the hill climb up to this point. And when do you stop? You don't see improvement, then that's when you stop. But then the issue is, where do I start from? And that's an issue with EM. EM is local hill climbing method, if you want to kind of call it that way, because you won't figure out, like if you start from here, you hit here, but you never know what the actual data maximizing, observed data maximizing parameter set is. Okay. That's it. I mean, do you have any questions? This is probably the one of the interesting things that you saw this course. We'll also see SVMs. I don't know if you've seen SVMs in 572, but we'll also try to understand SVMs in a better way, like this. Okay. So we'll take a break. Okay, so let's continue. So just again, high-level context. We had MLE problem, which seems one-off, and EM also seems one-off, but it's actually a very general tool, which may be needed if you want to have a very principled approach to your data. Okay. You can assume things like we just, in the mixture of Gaussians, we assume some Bernoulli to be present that was not observed. For example, let's say you have, this is just, I'm thinking on the fly. Let's say you had you were observing income, okay? But you can always, when I say hallucinate, you can always model it as you're observing income, but it's conditional on whether income of individuals, and it's conditional on whether they went to UIC or not, okay? And you don't have that information, okay? So that could be your delta. Delta is the probability that they went to UIC, probability that they went to, is the random variable whose realization for each individual could be whether they went to UIC or not, okay? Maybe you couldn't collect the data, maybe it's private data, okay? And you see your income distribution, it happens to be bimodal, okay? In the sense it's like a two Gaussian thing. Then then you can use EM to actually, given the data, what is the likelihood that somebody went to UIC or not? These gamma i's were actually the probability that somebody went to UIC or not, given all the income data and my current estimated parameters, right? That is a more principled way than to just say, okay, if income is high or low, just say somebody went to UIC. Is the example clear to some of you guys, or no? All I'm saying is the delta is, think of it as a binary variable indicating whether somebody went to UIC or not, and y is that to observe are income levels, or maybe not UIC. Somebody went to MSBA program versus non-MSBA program. You see income levels, and you can fit. Maybe maybe the data looks like bimodal, so you can fit a two Gaussian thing, and you can actually fit two Gaussian thing means get the parameter, which is pi, mu1, mu2, sigma 1, sigma 2, and given that you can say, now given that somebody's income is x, little y, I can tell what is the probability that delta is equal to 1 and delta is equal to 0, because I know the joint distribution. We wrote the equation for the joint distribution between probability that capital Y is equal to little y and probability that capital delta is equal to little delta. I know the joint distribution. So I can always compute all sorts of conditional distributions. If I observe little y, then what is the probability that capital delta is equal to little delta, right? So this is a principled way to do so. And that's just one random example I thought of the fly, but this is a very principled approach. Okay.
So in which case we will get like two Gaussian,
Doesn't have to do Gaussians, right? It can be a mixture of other arbitrary distributions.
So, I was just thinking like if, let's say we have a data for 1,000 students, but in between 4 observations are missing the information or something, at that time it's like break in between you might see?
No,
Visualize?
No, I didn't understand your question. The example that I gave was you don't have the only thing missing is the whole column, that you did not observe whether somebody went to UIC or not. The whole column was missing.
Let's say we observe 1,000.
Okay, so
We have 0, 1, 0, 1, whether they are.
Oh, you're saying you already observed deltas.
Yes, but we do not have information for like 5 students, 10 students.
What information do you not have?
Like
The
whether
income.
they are the student of.
Okay.
this
Oh yeah,
program
then the
or
same
not.
principle can be used.
So at that time, that's why we are seeing like one
No, forget about the break part. Data can be bimodal just because of, maybe if you mix rich people and poor people, then you may see two modes, right, of wealth.
So it's just two models, it's not because of what I've been doing, because of missing observation.
Yeah, it's not, the bimodal nature is not because of missing observations.
I'm just trying to
I mean, you
visualize
could
it.
have bimodal data because of missing observations as well, but that is not the context of the. But what I'm trying to say is, this is something that you probably want to kind of think about. If you had, let's say, incomes, y1 to yn, and delta 1 to delta n is what you did not observe. Maybe whether they went to UIC or not, or maybe they took the MSB program or not. Because of EM model, the way we have assumed the model, the mixture model, we can always estimate the probability of delta for, let's say, so this is the kth person. What is the probability that the kth person, let's say, went to UIC, given that their value, the observed value is YK, maybe their income level is $100,000. You can actually compute this because you know the whole parameter. You estimated the theta, right? That was the whole point of this modeling business. Once you know this, you can actually find this. Okay, so that's the use of EM, not just EM, but this sort of generative model, describing how the data got generated. Ultimate data that you observed was just income levels or just Y's, but you said that maybe they went to college, maybe did not go to college. Depending on that, something manifested. Maybe they fell into the first Gaussian income group or the second Gaussian income group, and so you can backtrack and find this. Another interesting thing that you can do with EM is, let's say you're missing, for the kth person, you're missing actually the income value itself. You haven't observed, you kind of you did survey, you got data for everyone except for the kth person, they did not report their income level. Okay. So this is a different example where, let's say, you did, you also surveyed whether they went to UIC or not, and you have observed deltas. You have observed deltas, you have observed Y's, but one of the Y's you have not observed. Okay. Even in that case, you can find the probability of Y equal to any value given that the delta is delta. Okay. You can fill in missing values. Okay. So how are you filling missing values before? You're probably deleting the row in your.
No, that's so. What
That's
I was
different.
thinking is way before even we have this mod.
Yeah.
If we have a missing value, then we replace.
So I'm saying this is a viable way to fill in missing values as well. What do you call imputation?
Yes.
I mean, don't get confused that this is the only way to do imputation or anything like that. I'm just saying that there's a very powerful model where you can really mix and match many different distributions, assumptions about things that you did not observe, how they may influence what things that you did observe. Okay. So as I said, supervised learning, we backtracked into MLE. We saw something about EM today. This was last lecture. Okay. Supervised learning, linear models. We saw MLE and Bootstrap, I guess. Last lecture. EM, and we'll see sampling. And then we'll get back to supervised learning track. Okay. That's the high level idea. Supervised learning with linear models, that's what we did earlier. Next lecture onwards, we'll look at supervised learning with more flexible models. Okay. In between, we are touching these topics. So let's pick up sampling. Sampling, sample is is a word which means a lot of things. I think in Bootstrap I said Bootstrap sample, right? And typically in supervised learning, I'll use example as the observation or realization as the row of your data, and the whole data could be considered as sample. Okay. But here, when I say sampling, I'm saying I want to get a realization from P of Z. Let's say P of X. I change the random variable. I want to get a realization from a distribution. Okay, that's all I want. And why do we need it? Why do we need it? As in, why do we need realizations from a distribution? That's the first question. And second thing is, how do we get samples? Right. So how many of you have actually seen something to do with sampling before? 4, 5, 6, 7, 8. A lot of people. So what did you see sampling for? I mean, in which context did it arise? Econometrics. Okay.
So, I guess just if we're setting an example of how education affects earnings. So
Yeah.
like a huge sample.
Yeah, the sample would be the data. I'm talking about sampling from a distribution, like a distribution X. Like drawing a random variable. Like, I don't know in R what the function call is. Like random dot R norm or something. I don't know what the function is actually. Yeah, when would you would have used that? Like maybe you use it to generate some synthetic data, experiments wise. Did you have to generate any synthetic data for any of your assignment questions? You always use some data like auto or some data set, housing data set or something like that, right? But what if you had to generate some data so as to see that actually regression works, even when it actually generated the data that the way you wanted, right?
Is that like in the example I think I saw where they have the orange and blue dots and
Yeah.
the two Gaussians and overlapping so you can see the base and the boundary?
Yeah. So they generated data. So generating data, they had to get a sample from one Gaussian and get a sample from another Gaussian, right? Let's say you knew you want to get a sample from a Gaussian. You know the mean, you know the variance. How do you get a realization, right? That's the problem of sampling. So econometrics fine. So where else have you guys seen sampling?
If you're splitting your training data up into your training validation and they call that sampling, I think that's a different thing that you're talking about. It's still randomly picking numbers and separating it, but I don't think that's too different.
Yeah. So that is not very core to this. So the simplest sampling thing is, flipping a coin, right? You want to get a Bernoulli variable, you want to get a realization of a Bernoulli variable, actually physically take a coin, flip it. You get some realization, that's your sample from a Bernoulli. Assuming the coin is fair, you get a sample from the Bernoulli, right? That would really be laborious. So there are computer ways to, there are ways to do it on a computer, getting a sample from a Bernoulli. In fact, I'll show you one example of how you can get a sample from a Bernoulli, just to kind of warm up. Okay. So I guess I'm addressing this part. Let me get to why we need samples. Actually, let me say why do we need to get samples. Bernoulli, Gaussian, those are very nice, simple distributions. For which you can actually probably compute functions of those distributions. What do you mean by functions? Let's say you want to compute the expectation of sine of x to the power 1 by 10. Okay. Somehow got something like this expectation with respect to a distribution over x, and let's say x is normally distributed. Okay. How do you compute this? You can do integration, right? I mean, the simplest thing is actually if p of x is normally distributed, then you know exactly what the formula is. P of x is equal to x. You know what the distribution is times the the function itself, sine x to the power 1 by 10 dx, right? Where you substitute that formula for Gaussian, right? And maybe integrate from minus infinity to infinity, right? This may be difficult to do in closed form, right? Because there's an e to the power term and a sine to the power something else. Maybe some rules of integration you can use to integrate this, or maybe not. In situations like this, samples come to the rescue. As in, you can't compute the exact integration here, so you wanted to compute this somehow, okay? But it's hard to compute. Hard as in, it requires integration, which I don't know how to do. there are computer methods to do integration. That's not an issue. But there is an alternate way, which is to actually just get samples, right? Little x1 to little xn. You draw from p of x. So you know p of x, let's say it's Gaussian. You want to get some n samples from the Gaussian, n examples from the Gaussian. And then you can just compute the expectation, approximate the expectation as 1 by n, sum over I is equal to 1 to n of sine of xi to the power 1 by 10. Okay. This is called Monte Carlo average. Okay. So this is one use of sample. So if you want to compute functions of some complicated distribution, or maybe the distribution is simple, but the function is complicated, somehow you can't do integration, then you can get samples, hopefully, from the distribution, and just evaluate the function at the samples, average it. That's what I'm doing here. Okay. Just one reason why we need samples. Yeah. Why are we averaging? No, we need a single number. This thing here. It's a function of the distribution. The claim is that this number that we are estimating, as n goes bigger and bigger, this number is close to whatever this number is. Okay. Actually, in the elective advanced predictive models course, there's this we were studying some object called generative adversarial networks. Okay, it's a fancy name for generating samples. Okay, so you can actually generate. So think of images, real world images. Okay, photographs, 100 cross 100 pixels. 1000 pixels cross 1000 pixels photographs. You have all this data, which are photographs, let's say millions of photographs. From that, can you learn a distribution of photographs and generate a photograph which is not actually clicked? Okay, you should generate an image, 1000 cross 1000 pixel thing, but it should not be actually from clicking a photograph. It should be a sample from this complicated distribution over images, and that sample should not be just a memorization, in the sense it may not be one photograph that you actually have in a database. It has to be a photograph which is generated from the distribution. So it could be as realistic as possible, but not clicked from a camera. So people are working on that now. Okay. Actually, there's this magazine called MIT Technology Review. So I think last month or this month, they had this 10 breakthrough technologies of 2018. So they keep coming up with 10 technologies for each year. So this year it's one of the technologies is this thing called generative adversarial networks. Okay. Just an example of sampling. They want to sample from really complicated objects. Here we just want to sample from actually random variables. Okay. So how do we get samples? So I was just saying for Bernoulli, let's say Bernoulli with parameter pi, what is it? X is a Bernoulli with parameter pi bias, right? One way to actually get the sample is flip a coin with that bias, but you need to have a coin with that bias. Maybe it's a fair coin. Then you have, let's say, for pi is equal to 0.5, you actually have a coin. You can flip it mechanically and get the sample. That's a tail or a head or something. But what if the bias is 0.9? What are you going to do? How are you going to bias a coin? Mechanically, maybe not. So I'll give you a way to generate Bernoulli or anything else. Not anything else, but some very restricted distributions. So we have to assume something, right? So let's assume we have access to U, which is a uniform 0, 1. Okay, So we have access to some subroutine, some function, which at least give us a random number between 0 and 1, uniform between 0 and 1. Okay. You have to start with some base object, so let's assume we have the uniform distribution. Okay. Given the uniform distribution, I'll give you a couple of examples of how to generate any probability mass function, and let's start with the Bernoulli. Okay. So we have a random variable. So the trick here, this is one. There are many methods to sample. So I'm going to give you this as a warm-up trick to get to what we actually want to do, Gibbs sampling. So here we have a random variable u. We want to get a random variable x according to some arbitrary chosen bias pi, right? So the natural way to do this is to relate the random variable x with the random variable u. U is what we have access to. So we're gonna relate it this way: x is equal to 1 if u is less than pi, u is between 0 to pi, x is 0 otherwise. So this is a function of a random variable, right? So it's saying if u takes a value something, x takes a value something. It's a weird way of writing a function. You would think, let's say, another example function would be x is equal to u square. That's a function. That's a more natural way to write a function. This is also a way to write a function. X is taking two values depending on what u is taking. Okay. Essentially, what we are saying in terms of pictures, we are saying u takes values between 0 and 1, right? U can be anything over here. U falls on this side, let's call x1. U falls on this side, let's call it 0, right? And so how do I generate a sample x? I generate a sample u, just compare it with some number pi, and this number has to be between 0 and 1. Compare it with pi. If it is smaller than pi, I'll call my sample x to be 1 or otherwise 0, right? So I created a sample for Bernoulli given just access to uniform. And to just check why this is correct, you can just find the probability that x is equal to 1. What is the probability that x is equal to 1? Is exactly, maybe you can write integration, exactly from 0 to pi, or the probability that u is equal to u, right? Right, x is taking a value 1 only if u is between 0 and pi. So I'm just integrating from 0 to pi of whatever probability mass is for this random variable, right? What is probability of u is equal to little u? Huh? U is a uniform random variable. So if you actually draw it, in terms of probability density function, it's going to take some value, right? Some value here. Some value between 0 and 1. So for each value, there will be some value here, right? Such that it integrates to 1. So what is the value? Yeah, area under the curve is 1. No, but what I'm asking is what is P of u is equal to any little u? It's just 1. Right? The area is 1. So this is 1. If I make the height 1, 1 times 1, the rectangle's area is 1. Right? So it may be confusing, but it's a little bit counterintuitive to think about it. But if it was a discrete distribution, if u was not uniform, but u was taking, let's say, n different values, and I said uniform of that, then the probability that it takes any of the n values is 1 on n. I think that's it. Anyway, in this case it's 1. So 1 times integration from 0 to pi du. I guess I brought out 1. I can just leave it here. This is just pi. Right? Pi minus 0, I guess, equal to pi. Fine, so at least we got we defined a function, we said this is how we generate a Bernoulli, and it is a Bernoulli because probability of x is equal to 1 exactly is equal to pi. This one. This is the EU. This is also the EU. Anyway, I mean, I just wanted to illustrate, and this concept you can extend it to any discrete distribution. So although my base object was a uniform distribution, continuous distribution, I can generate any arbitrary PMF. So let's say I had a random variable which takes 3 different values. Okay, here the random variable x takes a value 0 with probability 0.3, takes a value 1 with probability 0.2, takes a value 2 with probability 0.3, and what is left? 0.2. Okay, this is not even. Let's make 3. Let's make it 2. They're on the same height. Okay. Let's make it the same height. 3, 2, 2. 0.2. Okay. Maybe the random variable takes 4 values. So how do you find? How do you draw a sample from this PMF? You're gonna again do the same thing. You're gonna break 0 to 1 into 4 parts. So you'll start with this one as some interval. This is 0.3. Next interval will be 0.6. This will be 0.8, and this will be 1. So I'm just adding these two and made it 0.6. I add the first 3 and made it 0.8, and the full thing is 1 anyway. So I'm saying that I draw a uniform distribution, uniform random variable realization. Depending on where it falls, I'll just call it x is equal to 0 or 1 or 2 or 3. Okay. So that's a way to generate a discrete arbitrary PMF with finite support, as in like finite values, given access to a uniform distribution. Okay. Just some simple tricks of, if somebody asks you how do you sample, like at least you can give these examples. I mean, there are many more complicated ways people have figured out, and on a computer there's pseudo random number generators which generate random numbers which will kind of simulate this uniform access to a uniform distribution. That's what they do. And on computer, as in R or Python, you have these functions, random.rnorm, runif, things like that. At least for simple distributions. And here I'm saying, if you wanted to create an arbitrary PMF and get a sample from there, you would use runif or something, and then maybe write a if else condition like this, given the realization of from runif, and output the value of your random variable x. Okay, so that's fine. Any questions at this part? But in general, so what I'm trying to get to is a particular sampling method. Okay, so there are many sampling methods. It's a huge field, but in this course, we're going to look at one sampling method which is pretty popular, called Gibbs sampling. Gibbs sampling. And it's applicable for any distribution x. As you know, it can be quite complicated. So think of a distribution over 100 dimensional random vector, where if you draw a histogram in each dimension, each curve looks like very arbitrary. It looks like a messy. Each one dimension looks like a mixture of Gaussians. Then you can imagine what the joint distribution will look like really complicated thing, right? What I'm saying is, think of very complicated distributions. We can get a sample from them as well. Okay? In fact, sometimes sampling is the only way to do anything with these complicated distributions. Okay. For example, think of this. We had this Bayes rule, right? Probability of theta given, I guess, data is equal to probability of this data given theta times probability of theta, some prior, divided by probability of data, right? So this is the posterior, okay, and this object p data. So I'm using data, just think of, let's say data is x. Okay. So probability of x is actually integration of p of theta given data. So I'm just taking x to the left hand side, and left hand side I want to bring it down, down. So p of x given theta times p of theta divided by p of theta given x. Oh, this is not useful actually. Okay, this is not useful. Times d theta. I mean, here I just said, you know that this thing inside p of x given theta times p of theta is just p of x comma theta. We know the joint distribution between two random variables just splits as one marginal times one conditional. And here, I mean, so all I'm saying is, and this is a marginal distribution, p of x is just the integrate out the second random variable. That's what I'm doing here. Integrate out the second random variable over the joint distribution, right? Do you guys agree with this formula? So you can see that if I want to compute the probability of x, it requires an integration, okay, over something else, some theta. Maybe if theta is, let's say, 10 dimensional, like mixture of two Gaussians had theta 5 dimensional already. Mixture of 10 Gaussians, you can imagine it doesn't just in one dimension. Okay, mixture of 10 Gaussians in one dimension is going to have too many parameters, and you can imagine in very high dimensions it's too many parameters, right? So to you can also, again, once you see integration, you should kind of quickly think, okay, if I have integration, I can approximate using Monte Carlo average, right? So I can get samples x for any given theta, if I can get samples of x, and if I can get samples of theta, right? I need to sample theta. So how do I approximate this? I actually sample theta. It's an integration over theta. The expectation is over theta. This is I get a sample from theta, right? That's what I want. If I can get 10 samples from theta, that I can just average. I can do a summation of p of x given theta is equal to theta I. Sum over I is equal to 1 to n, 1 by n I. So my Monte Carlo average here would be something like this, right? I sample n different theta values, if I can, and then I can compute this. So this is easy because I just have to evaluate the probability that x takes a value x given theta is equal to theta. That's, if I have a closed form expression, I can just evaluate that expression. This integration was the one which is problem, right? Anyway, and p of theta can be complicated. Okay. So anyway, coming to Gibbs sampling. So in the previous, simple example, so this is just an example. In the previous example where I was creating from uniform, I was creating arbitrary distributions. I would draw a uniform. I get an x value, sample of x. I want another sample of x. I'll draw another uniform and get another sample of x. These two are independent. I get two different independent uniform draws, and then two different x's. So one x is not related to the other x. One sample is not related to the other sample. Okay. But with high dimensions, there is a class of techniques which are called Markov chain Monte Carlo. Actually, which is the order. Okay, I don't know. Yeah, Markov chain Monte Carlo. Okay. and what they do is they will generate samples. So in this case, little x1 to little xn, or in this example you are supposed to get theta 1 to theta n, but anyway, if you have a distribution x, you can get samples x1 to xn, but these x1 to xn will be not independent. Okay, they'll be somehow dependent. Okay, so let's say little x1 to little xn are the realizations. You can kind of imagine that there's, if they're realizations, there's a corresponding random variable to them. These capital x1 to capital xn, you can think of random variables, these are dependent. Okay, it turns out to be that this class of families create samples, but these samples happen to be dependent. But they are a really good way to create samples. That's why we are studying them. Okay. Why are they called Markov chain Monte Carlo? How many of you have heard the term Markov chain? One, just one. Which course? Or somewhere? Where?
Somewhere probably.
Okay. What about you guys?
I've just heard of it, but I never worked with it.
Markov chain?
Just
Okay. It's cool names, right? People give chains and something else. So Markov chain is just, it's basically some kind of okay. So let's say that three, in this case, let's say they're random variables. In fact, x1 to xn are the random variables. Markov. So first, let's understand what Markov assumption means. Why use the word Markov? Markov is just kind of a name to say memoryless, or it's basically, think of, let's say there are n random variables, and we have distribution which is p of x1 to xn. Okay. What is it? Then Markov just means probability of x1 to xn, just splits as probability of x, I guess j plus 1 is only dependent on xj. Okay. Markov just means that the probability of so remember, if you had a joint distribution, you can always decompose it into a factorized distribution, right? Probability of so you can write this as probability of x1 times probability of x2 given x1 times probability of x3 given x2 comma x1 times probability, you can do a lot of probabilities. Let's say probability of xn given xn minus 1 all the way to x1. Do you agree? This is just a this is a rule, a fact. Okay. All I'm saying is, if you look at the third term, x3 ideally has to depend on x2 and x1, but I'm saying x3 only depends on x2. It's memoryless. Given the previous random variable, you don't care about all the other previous random variables. Okay. It only depends on one step, and that's called the Markov property. Okay. The word chain just means we're getting samples, right? They are like one after the other in a successive manner. That's why they're saying a chain. But let's describe what Gibbs sampling is. We'll not really look at the we'll not actually look at, so Markov chain is actually an object that underpins Gibbs sampling, but we'll not look at what Markov chains exactly are. I mean, I just told you what Markov property is, and I just said chain roughly means something to do with getting more and more samples, but that's not the whole picture. Markov chain is a whole theory and so on, and it's an interesting object. But let's directly look at what is the Gibbs sampling procedure. Okay, let's try to understand how do you get samples with high dimensions. And there's no secret sauce actually. Just like in the previous case, we assumed access to the uniform distribution. Here we'll assume access to conditional probability distributions. The probability of, so let's say X is p dimensional, right? You know, like our input feature vector is p dimensional, X is p dimensional. Then I want to say I have access to all conditional probabilities. Probability that X, capital X, these are all random variables, capital X j given capital X1 to capital X j minus 1, comma capital X j plus 1 to capital X p. Okay, what I'm saying is, given all the other coordinates of my random variable, I know the conditional probability of the left out coordinate. For every j, I know this. I assume access to this for j is equal to 1 to p. Okay, this seems like a very strange thing. I'm saying I know the conditional probability of each coordinate given all other coordinates. Okay, it turns out that this conditional probability is a easy thing to compute if you know the joint distribution of, if you know p of x, then getting this is easy. Okay, to this is easy. So let's not worry about how we get from p of x to that for now. Let's say I have access to this. Then Gibbs sampling is a procedure which uses these and says do the following. Okay, for that I'll just show you what the procedure looks like. So think of so p dimensional, let's say p is equal to 3 for us, example, which means I need to let's say I want to create observation 0, observation 1. This is the observation number 0, 1, 2, 3, and so on. So what Gibbs sampling says is let's start with some arbitrary value. Okay, some number, let's say 5. So p is 3, that's why I put 3 dimensions here. So think of this as x1, x2, and x3. Okay, so this will be little x1. The row would be little x1, the first sample. The second row would be the second sample, like little x2. Okay, let's call it x0, x1, x2. I mean, 0th observation, first observation, second observation, so on. Okay. So let's start with filling in the first number for the first. I'm creating the first observation now. Okay, and the intuition here is going to be I'm going to create the observations coordinate by coordinate. Okay, so that's why I'm thinking of like a conditional probability of a coordinate given every other coordinate. Okay, and I need to start somewhere, so let me put a number 5. Okay, let's say x can take value 5, and let me put some number there. Now yeah, let's say there are already some numbers. Okay, let's say there are already some numbers. Let's say I have a 0th sample for now. I mean, I'll tell you how to start it, but it's not a big deal. Let's say I have let's say I have the 0th sample. So how do I generate the first sample? Okay, it's going to be, as I told you, samples are going to be dependent. These observations are going to be dependent. The first sample is going to be sampled from this conditional distribution, which is at the top right here. Probability that the first coordinate is 1 given the other coordinates, but the other coordinates are not filled up yet, right? So what I'm going to do is I'm going to use the previous values, the values 3 and 4. So to fill this guy, let me fill this question mark here, I'm going to draw a sample from x1 given x2 is equal to 3 and x3 is equal to 4. These were the previous samples, x2 and x3. X2 and x3, yeah, 3 and 4. Right? I'll get some number here. This is the question mark. Question mark 1. Let me not put 1 at all. Question mark, I'll get that. Okay. And now double question mark, I'm gonna get by, let's say the question mark realized to be something. Maybe it was 1. Okay, let's say that number happened to be 1. The double question mark is going to be sampled from probability of x2 given x1 is equal to that value 1 and x3 is still the old value 4. Okay. I'm just filling these, creating these observations coordinate by coordinate using these conditional distributions, and wherever I don't know the values of the conditional distributions because I've not gotten any information of them yet, I'll just use the previous observations values. That's why it's the observations are dependent. Okay, and it's Markov because it's not dependent on 2 observations ago. It's only dependent on, at most, on the previous observation that you can see. Okay, that's how you do it stepwise. So that's how you maybe triple question mark, you figure out something and so on. Is the procedure clear? Is the procedure clear? This is a Gibbs sampling is quite simple, and it's very, very powerful technique because I said if you have a complicated distribution, turns out that computing these conditional distributions are easy. And just to see that, what is the conditional distribution of P of xj given everything else, x1 to xp? I mean, of course, not including xj. It's just going to be the joint, which is P of x, divided by the marginal, where you just sum over x, the jth guy, xjth guy of P of x, right? Remember the conditional a given b is just a comma b, which is numerator, divided by sum over sum over a of P of a comma b again, right? What I'm saying is finding the conditional distributions for by just doing one summation is easy, because one coordinate it's easy to sum. Okay, because one coordinate is just one number, whatever values it takes, it's easy to sum. Anyway, so don't worry about this part. All I'm saying is if you have access to this, Gibbs sampling generates samples. And what I have not shown you, of course, I just showed you the procedure of how to get the samples. We have to say that why are these samples x1 to let's say xn, why are they actually from P of x? Because I'm not actually using P of x. I said I only have access to conditional distributions. I'm creating this step by step, coordinate by coordinate, and still these samples, although dependent, are going to be drawn as if they are drawn from actually P of x, because we wanted samples in P of x, right? For that, you need to know what is meant by Markov chain. What is meant by Markov chain and what is meant by a stationary distribution of a Markov chain. It turns out that there is something called a Markov chain whose stationary distribution is P of x. Okay, and in this case, Gibbs sampling is a Markov chain whose stationary distribution is P of x. So what happens with Markov chains is eventually you get samples from the stationary distribution. Since Gibbs sampling's stationary distribution is P of x, you get samples from P of x. I will, because it's not necessary for this course, I don't want to get into Markov chains here. All the previous coordinates, which is only up to previous. Yeah, but these, okay. So here what I wrote was, so think of these x's as vectors. So, okay, if you want a consistency between what I wrote here and below, just think of Markov chain need not necessarily say just the previous random variable. You have to have at most, so think of, so in the Gibbs sampling procedure, I'm only having dependency on the at most p previous values and no values before that. So it need not be just previous one, it can be previous p. Yeah, p is, I mean, x is p dimensional, x is p dimensional animal. Yeah. 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 So there's, okay, here if you want the actual picture, the Gibbs sampling is per coordinate. These x's that I wrote are actually samples themselves. So these are, each x here is a vector. If you're getting confused with what I wrote here and later, remember I had to create these samples little x1 to little xn which are vectors, p-dimensional vectors. I said the corresponding random variables, let's assume to be, I guess, overloading of notation, capital X1 to capital Xn. So maybe I should put underbar here. These are vectors. And these what I said is are just dependent on at most dependent on the previous observation. Okay, let's put underbar here. Just to differentiate them from coordinates. So here, when I in Gibbs sampling, what I said is these are coordinates of a single vector. Okay. So this example that I just gave about, think in terms of what is meant by Markov. This is for the whole vector, because each realization you can think of, it corresponds to an actual vector, random vector, right? We can discuss this more if you want. Okay, I had one small piece to further discuss, but that's actually related to supervised learning, called generative. What is it called? Generalized additive models, but I'm gonna discuss it next class, okay? Because it's consistent with what we're gonna. In the next class, we're gonna again, we're not gonna touch these things. We're gonna come back to supervised learning world. Now, but then move away from linear models to more flexible models. Okay? That's what's going to be the next three lectures. Okay? That's it for today.